Thank you very much for the invitation. It's really a great pleasure of being part of this event. Okay, as maybe some of you know, there's quite some effort in Europe in say setting up, say, a pan-European HPC infrastructure, which is in parts funding by the European Commission, and it has, say, several legs. I mean, one is the build-up of, say, an infrastructure, but it's also about the development of future technologies, but it's also, say, doing work on applications. And I will touch a little bit, even so it's not the focus to introduce, say, this new organization called Euro HPC here, but I will touch on these different aspects throughout this talk when I say start with, say, talking about the emerging Euro HPC infrastructure and what kind of portability challenges emerge from the way of how this infrastructure is now being implemented. And I will also here give you a little bit of an outlook in terms of European technologies which are currently being developed. And then I will focus mainly on, say, the application development strategies, and here touch on the work which is done in the EU-funded Centers of Excellence. That's, say, are organizations which focus and are supposed to keep the competence on different science and application domains before I then, say, conclude with a final discussion. So let's look into the emerging infrastructure. So what currently is happening is that there are 3 pre-Exascale systems being deployed. The first here in this list is actually almost completely in place and operational. That's Lumi in Finland. And it comes with a very large GPU partition where each of the nodes comes then with 4 AMD MI250X GPUs. Now there's a second system which is currently being, say, deployed in Italy at Cineca, and it comes with a very large number of NVIDIA A100 GPUs. So here we see already that we have systems with 2 different types of GPUs, and then you see already, say, this portability challenge emerging. And there is now a third system which is also coming. Their contract has, say, quite recently been awarded, and so it will be able then to make then a technology jump, and it will then directly jump to the next generation of NVIDIA GPUs from the Hopper GPUs, and it will also include then an experimental partition using then NVIDIA Grace superchips. So that means we also have, in terms of the CPUs, we see here, say, an emerging diversity, as we have then, say, systems with x86-based CPUs from Intel and AMD, as well as then also ARM-based CPUs from NVIDIA. Now, there's a second tier of so-called petascale systems. That's an overall 5 different systems. I don't want to go to all the details. They are spread all around Europe, but I just want to highlight, say, the Portuguese system, because on the one hand, it has also there a GPU accelerated partition, again, with NVIDIA A100 GPUs, but it also comes with a partition based on Fujitsu's A64FX processor. So that means that we have, say, here yet another system where we have ARM-based CPUs. Now, when we look further out into the future, the European Commission has an agenda about, say, European digital sovereignty, and an important part of that is also to try to re-establish server CPU development within Europe. And this is happening in a project which is called the European Processor Initiative, which is currently developing a platform with different chiplets, and so it's a heterogeneous, say, setup where, say, some of the chiplets can be based on general purpose CPUs with ARM Zeus cores. So again, you see ARM, and here I would also like to highlight that it's not just ARM, but it's ARM plus their new SIMD instruction set architecture, the scalable vector extension, short SVE. And it will also, say, allow to integrate then chiplets which are then based on accelerator technologies. And one of the accelerators which is currently developed mainly at BSc is the RVV accelerator. So it's the RISC-V vector accelerator based on the RISC-V vector instructions. Now, these are, say, really long vectors. So the intention is to have here vectors with a length of up to 256 doubles. We see here then yet another instruction set architecture emerging. We see here yet another, say, not only SIMD instruction set architecture, but also vector instruction set architecture. So again, we see more, say, diversity in terms of the architectures, and therefore also then more portability challenges emerging. So just to summarize that, I mean, where do we have the portability challenges? On the one hand, we have them when it comes to SIMD or vector parallelism, where we have then different SIMD as well as vector instructions with different widths. So in this, for the SIMD instructions, say, as far as it's currently, say, the plan of record, something between 128 and 112 bits. And for the vector instructions, I mean, if you translate the 256 doubles into bits, just to make it easier to compare, it would be then more than 16,000 bits. Now, an interesting feature both of the scalable vector extensions from ARM, so SVE, as well as the RISC-V vector instructions, is that they come with an, say, special feature which is called vector length agnostic. And that means that the instruction set architecture, unlike, for instance, AVX or AVX 512, which prescribe a certain width, here for these instruction set architectures, there is no width which is prescribed, and it depends on the implementation of how wide the SIMD operands are or how long the vectors are. Now, secondly, we have then, say, the portability challenge in the context of the compute accelerators. So we have different, say, GPUs becoming available. And additionally, we have the diversity of programming models. And if we look at, say, the current state of these programming models, I mean, they lack coverage. I mean, essentially, none of them is really covering all of the upcoming, say, accelerator architectures. And there is another challenge, and that is, I would call it, say, a sustainability and support model challenge. I mean, if you look from the applications perspective, I mean, you would like to see these programming models be, say, stable, available, and well supported over very long periods of time. And that's not necessarily clear for all of the programming models. And also, if you look at the support models, part of them have a commercial backup, but part of them are also, say, developed in the academic environment. So also there are, say, uncertainties in terms of what is actually the support model. Where can I, on which door can I knock if there are issues with, say, these programming models? So that, of course, then asks for, say, developing, say, strategies of how to deal with these challenges. And for this section, I actually started off by looking what are the kind of applications which we are, say, currently providing to our users here at PDC, more specifically on our new system, which is Dell, which is also hopefully soon going to comprise with a significant GPU partition, like Lumi. It's also based on the AMD MI250X GPUs. And it's one of the, say, most powerful systems which are currently, say, available in Sweden. So, I mean, if I look at our system, then it largely reflects the needs of the Swedish community. So the application areas which we are currently, say, serve is in particular, say, the computation of fluid dynamics and engineering, and that comprise, for instance, applications like NAC 5000. I highlighted this here because I will come back to that later, but also OpenFOAM or ISV applications like ANSYS Fluent. We have a very strong biophysics and genomics community here. In particular here, the reference, of course, GROMACS, where, say, a lot of the development is happening in the Stockholm area. Then you have a very strong material science community in Sweden, and computational chemistry community, and a bit smaller, but also growing brain research community. So this gives already, say, quite large bunch of applications. I should, however, notice there are some gaps. Currently, we have in our system hardly people which are doing, say, Earth system modeling, or also, for instance, climate modeling or weather forecast, and also the more fundamental physics applications, for instance, in the area of elementary particle physics or astrophysics. But still, I think it's quite a representative set of applications. And where I was looking for is what is the current support for ARM-based architectures, and more specifically for SVE and GPU accelerators, if I look in all these applications. Now, let's look in this table what is the outcome of this, say, small survey. I mean, it's a total of 25 applications, and I categorize them in terms of, say, completely open academic codes, so where you can easily go to Git repository and check for the codes. Then say there, I put it here in quotes, closed codes in the sense of that they are not, say, fully open, so you have to register and you have to ask for a specific permission to get access to the source code. And then, of course, you have the ISV codes, which are, say, not open. Now, if you look out of these 25 codes, I mean, for which of these codes are there reports available that they actually have been used on ARM-based platforms? And it's a bit more than 50%. So it's in total, I could identify, say, certain codes where they actually are, say, running on ARM. And for 8 of these codes, I mean, I could identify explicit indications that they are using ARM in combination with SVE that typically means that they have been ported to the Fugaku system, so the Exascale system in Japan based on the Fujitsu-A64FX processor. Now, when we look into, say, the support of accelerators, now there's actually a non-negligible part of the codes which have no support for GPUs at this point, which if we look at, in particular, also say almost 50% of the ISV codes, which is not particularly surprising. I mean, I was actually surprised that this fraction is say relatively not higher. It's less than 50%. Now, if we look then of how many of these codes have been reported to be running on NVIDIA GPUs, then you actually see that it's indeed, say, currently the focus is on having these codes running on NVIDIA GPUs, and only for a few codes. I mean, there are, say, reports available where you can see traces in the source code that they have been ported to AMD GPUs. So that means that in terms of the currently available, say, production codes, there is a rather small fraction which really has, say, mastered the challenge of getting portability to this new generation of GPUs. Now let's look into, say, 2 codes more specifically and what have been, say, the porting strategies. And of course, not surprisingly, I went here through the codes where also PDC is quite heavily involved in developing these codes. Let's start with GROMACS, which is the same code which is leveraging, say, really modern C++. So it has over the time seen quite a lot of code refactorizations and modernizations, and it has been over time really be optimized to leverage, say, the different levels of parallelism, say the node level or system level parallelism through NPI, say the core level parallelism in OpenACC, but also then when you go to the core level using then also the SIMD instructions in, say, an efficient way. And it's also, say, working now with different programming models. So quite a number of the kernels have been, say, optimized using CUDA or even parts in OpenCL. But there's now recently a trend to move more to SYCL in order to also be able to support then the upcoming GPUs. In particular, for instance, now the ones from AMD, and then one either uses one API or then for the AMD HIP-SYCL. And here I would also to highlight, for instance, now the support challenge. HIP-SYCL is, say, a software which is developed by the University of Heidelberg, so it's not a commercial code, and that means that we have, and that's here also then, say, director of the supercomputing center speaking, we have, say, here not a very well-defined support model, and that, of course, is a bit of a possible risk, and that's something where the application developers have to be aware of. But it's a very high-quality code, so I mean, the GROMACS developers are, say, very happy with that. Now, one of the strategies of GROMACS in order to be able to deal with this heterogeneity has been to really, say, conceptualize, say, this way of how to deal with, say, the task of loading and to have, say, the right constructs to control the CPU accelerator data movement. And to control the asynchronous scheduling of concurrent tasks as well as their synchronization. So all that has been, say, put into a quite good abstraction layer, and I put here also, say, a reference of to a paper by Szilárd Pál and colleagues. Szilárd is one of the PDC developers. We described in this paper quite nicely of how that the code has been, say, refactored in order to be able to cope with these heterogeneous portability challenges. So what you have today in GROMACS is then that there's a directive-based scheduling for the different tasks and for then standard numerical tasks. I mean, things are offloaded then to libraries, for instance, if it comes to fast Fourier transforms. And then you have the optimized kernels, which are, say, implemented, for instance, in OpenACC, SYCL, or other proprietary low-level languages. But of course, the way of how this is done is that, say, these code parts are very well confined, so that even if you are, say, working here with proprietary languages, or maybe also, say, programming environments which are maybe not that well supported, then this is a manageable risk. And what I copied here is, say, here specifically to also have an outlook on how that works on, say, not that widely used GPU architecture, namely the AMD GPUs. You see here, say, in comparison from what can be achieved using, say, where the baseline is a proprietary language, it's HIP on an MA100 GPU, and then there's comparison is here done with using SYCL, and you can see here that in this plot that for, say, the whole application, depending on the system size, I mean, there might be still quite a significant overhead, but from the kernels itself, I mean, say, a pretty similar performance can now be achieved then for when using, say, the proprietary low-level language HIP. So that is quite, say, an encouraging result, and that has been, say, part of a presentation which was given at the recent ISC conference. Now let's look at another application, and that is the CFD application. So NAC 5000 is quite different in the sense of that it has a much longer history, and it's really say a typical legacy application written in Fortran 77, but it has been, say, really optimized from the very beginning for, say, extreme scalability. It was also it did win at some point in the Gordon Dahl Prize in at the end of the 90s. But given, say, this legacy, I mean, it was quite difficult to get actually these codes onto into a stage where it can leverage, say, GPU acceleration. And there have been several efforts. Part of it also, say, complete re-implementations. But there also have been some work, and part of it was also where, say, people at PDC have been involved. So I show here, for instance, some work of John Vincent and others. He presented the results at the HPC Asia conference at the beginning of this year, where OpenACC was used actually to port NAC 5000. And the experience was that, say, in order to reduce some of the negative performance impacts, say, code changes were required. So it was not just about adding some directives, but you had to touch the code. Also, in order to really achieve the right performance, some of the kernels had to be implemented in CUDA Fortran. And it was also observed that in some cases, OpenACC turned out to be a bit too conservative when it comes to data management. But overall, I mean, at least if we stick then here to different systems, as you can see here in this plot, all based on NVIDIA GPUs in parts of the voltage generation, and then or a Pascal generation, and the others are mainly on the Ampere generation. You can see here that there's quite a nice portability onto these different systems. So in particular, say the green ones is, for instance, Pitstein at CSCS based on Pascal GPUs, and say the most recent system, the Jules Booster, which until recently had been the fastest system in Europe based on the NVIDIA A100 GPUs. Now, this is, of course, a bit limited in terms of portability. So that's why Niklas Jansen, who is another member of PDC, started to an effort of a full re-implementation of NAC 5000. And one thing which I like very much about his effort is that, say, while you see often, say, a trend in terms when it comes to a re-implementation of these applications, of say, legacy applications, moving, say, from Fortran then, for instance, to C++, he made the decision of sticking to Fortran, but of course modernize it now to Fortran 2008, and to continue to basically leverage what he considers to be, say, a very successful aspect of NAC 5000, namely to have, say, the core part of the application being implemented in well-supported high-level languages, right? C++ would of course also be a good choice, but since the community is also very much still using Fortran, Fortran was in this case probably a better choice. And what he could demonstrate also with the way of how he did this refactorization, that you can reach this necessary level of abstraction, which is necessary for, giving, portability. And it is mainly centered around having a suitable abstraction for the key numerical task, which is solving, a linear equation as it is shown here, but still have a lot of flexibility of supporting, polynomials of different orders. But then also to have, device abstractions to hide, the memory management, and then to allow for then specialized implementations in the backend. So here you have then the similarity then also to GROMACS. So when it comes then, if you go down basically towards, a backend, then you allow for specializations, and that's where you can also then allow for, proprietary programming languages. And as it stands as of today, I mean, there's of course the support of different CPU architectures, also including the ACE64X. All that is based on plain Fortran 2008. But then you have the more specialized backends. So for instance, for the NVIDIA A100, it's using CUDA. For the AMD, it's using AMD GPUs, it's using HIP. And, but then also for instance, vector architectures like the NEC XX Aurora, it's using a combination of Fortran and NEC directives. And that's probably then also a very direct path then to support, for instance, the EPI RISC-V vector accelerators. But then you can even get more exotic and look, for instance, for FPGAs using that an OpenCL backend. And as you can see here, I mean, that's a picture from a presentation Niklas gave in a seminar in November last year, that you can really then reach portability to this vast diversity of different architectures. So let me come then to discussion about what can we learn from these different examples. Now, in terms of the uptake of, programming models, when we look at, vector assembly parallelism, I mean, if you look at the different applications, then what we can find is that applications mainly rely on compiler auto-vectorization, maybe with some guidance with, so for instance, OpenACC directives or proprietary directives, for instance, for the NEC compilers. And I think this is a very good strategy because I've done together with a PhD student, Bine Brank, recently a reassessment of where do we stand in terms of auto-vectorization capabilities. And I put here a reference to a paper which had been accepted for a workshop for the upcoming Cluster 2022 conference. Where we look very specifically for, SVE vectorization capabilities, and that proves for different compilers really very, very good. I mean, it makes an excellent use of the different features of the language, not only for arithmetic operations, but also for gather load instructions. And what I observe, to be rarely used is, for instance, the use of any kind of SIMD libraries. Now, when we look for the compute accelerators, I mean, we see here that there is still, it seems that, the proprietary programming languages like CUDA and HIP are dominating mainly for, really leveraging, the performance. But you see also, pretty reasonable use of directive-based programming models, where most widely it's then OpenACC, which is being used. But there's also, traction for SYCL. So that's definitely something to look on. And I think, I mean, this is not something where we claim this is, really proof, but there's, some loose correlation with, this choice with also the maturity of the development environments. Now, for most of the ISV codes, we can see that they are not available for a large diversity of architectures, but here one has to be also aware this is not necessarily a porting challenge. It's also a question of whether an ISV really wants to provide support then for different versions of the codes. And if you then more specifically look into NECO and GROMACS, they show a strategy which I think is really a good recipe for being successful, as they both feature clear separation between the front end and the back end, and then using established high-level languages for the front end. So for instance, C++ in the case of GROMACS, or Fortran 2008 for NECO, and then to allow for proprietary programming models when it comes for architectural specializations in the back end. So then you can support a diversity of architectures. You can optimize for performance as much as you like, But then it's of course important in order to be able to facilitate this split between front end and back end, that you have, say, suitable abstractions for not only the computational task, but more importantly also for the data layout and data management. So to conclude, so the foreseeable evolution of the European HPC infrastructure confirms, say, and also what we see on the global level, and trend towards more architectural diversity. I think what we also see is that a large fraction of the use codes are not necessarily well prepared for this diversity, so there's still a lot of work ahead of us. And for this challenge, it's really having, say, robust and sustainable programming models are really important for addressing this challenge, because you cannot expect that there's one programming model that fits all. And so we really also need to have design strategies that mitigate the risk when, say, using these different programming models. And so one way of doing it is to have, say, a clear split between the front end and the back end, so that you have, say, the suitable abstractions, which then allows you then to confine, say, the more specialized code into smaller code sections, so that if you have to change your programming models, that it becomes an affordable effort then to move to new architectures.